Hello and welcome to the Unit 7 Section 3 video on parallelograms. So in this section we're going to start talking a little bit more about quadrilaterals. As we've mentioned, any polygon with four sides is called a quadrilateral. That is the generic term for something with four sides. However, some quadrilaterals have special properties, and these special quadrilaterals are given their own names. One of those is a parallelogram. A quadrilateral with two pairs of parallel sides is called a parallelogram. That's where it gets its name. To write the name of a parallelogram, we use a parallelogram symbol, very similar to how we used a triangle symbol. So here's an example of a parallelogram. We have a parallelogram with sides AB and CD parallel, and we also have sides BC and AD, or DA, parallel as well. And that's enough to call it a parallelogram. So let's talk about some of the properties. If a quadrilateral is a parallelogram, then its opposite sides are congruent. So the length of AB and the length of CD are the same, so are BC and AD. If a quadrilateral is a parallelogram, then its opposite angles are congruent. So angle B is the same as angle D, angle A is the same as angle C. If it's a parallelogram, then its consecutive angles are supplementary. So the ones next to each other are going to add to 180 degrees. So A and B add to 180, B and C, C and D, D and A. If a quadrilateral is a parallelogram, then its diagonals bisect each other. So if we were to draw the two diagonals in this parallelogram, then AZ is the same length as ZC, and BZ is the same length as DZ. Okay? So those are just some of the properties of parallelograms. So we are going to use those properties to talk about doing a proof. It's been a little while since we've done a proof, but let's talk about a proof here. We want to show that JK, which is here, is congruent to LM, which is here, and that KL is congruent to MJ. So what we want to do is show that if we have a parallelogram, that the opposite sides are congruent, which is one of the properties. In fact, it's the first property that you have listed. So we're going to prove that. So we start off with JKLM being a parallelogram. That's given. We know that JK is parallel to LM and that KL is parallel to MJ because that is the very definition of a parallelogram. Definition of parallelogram. Okay? Now we know that angle 1 and angle 2 are going to be the same. So if we draw this diagonal here, JL, we know that angle 1 and angle 2 are congruent, and angle 3 and angle 4 are congruent, because if we extend JK and extend LM, then what we have is alternate interior angles. And we know that alternate interior angles are congruent. That goes back to Unit 3. So alternate interior angles theorem. Now we also know that JL is congruent to JL. It's congruent to itself. That would be the reflexive property. So let's put that in here. Now, triangle JKL is congruent to triangle LMJ. Remember, we're going back to what we know about triangles to show things. And we know that because we've shown angle 1 is congruent to angle 2, angle 3 is congruent to angle 4, and the side between the angles is congruent. So that is angle side angle. And so we can say that JK is congruent to LM and KL is congruent to JM, because what do we know about triangles that are congruent? Corresponding parts of congruent triangles are congruent. CP, CTC. All right, let's look at a more practical example. In CDEF, DE is 74, so DE right here, this is 74. DG is 31, So I'm going to write that there. And FCD, this whole thing, is 42 degrees. So we want to find each measure, starting with CF. Well, we know that if DE is 74, CF is also going to be 74, because the length of CF is equal to the length of DE. So therefore, CF also has to be 74 millimeters. And remember, when you have units, include the units. Now the measure of EFC, that would be this angle right here. Well, we know that consecutive angles in a parallelogram add to 180. So the measure of angle EFC plus the measure of angle FCD, which is 42 degrees, has to equal 180. And if we subtract 42 from each side, we get that the measure of EFC is going to be 138 degrees. And then finally, DF. Well, we know that DG is 31. So DF, because the diagonals are bisecting each other, is going to be 2 times DG, which is 2 times 31. So DF is going to be 62 millimeters. In example 3, ABCD is a parallelogram. We're going to find each measure. So let's start with AD. Well, we know that we need to find X. AD is going to be the same as BC. So if AD equals BC, well, AD is 7x, and BC is 5x plus 19. If we subtract 5x from each side and divide by 2, we get x is 9.5. Then we can just substitute that back in for x. AD is 7 times 9.5, and that's going to give us 66.5. For the measure of angle B, well, we know that the measure of angle A plus the measure of angle B is going to be 180 degrees. So A is 10y minus 1. B is 6y plus 5. And we know that's got to equal 180. So that gives us 16y plus 4 equals 180. 16y, subtract 4 from each side, that gives us 176. And then divide by 16, we get y is 11. And then here it's just a matter of filling in y, putting y back in to find b. So the measure of angle B is going to be 6 times 11 plus 5. So that's going to give us 71 degrees. All right, example 4, we're back to doing another proof. So let's see what we get when we do this proof. We want to show that BAD, which is here, is congruent to DCB, which is here, and that ABC is congruent to CDA. So we're showing that the opposite angles of a parallelogram are congruent. This is what we're proving. So we're going to take that ABCD as a parallelogram. That's our start. Well, we know that AB is congruent to CD and DA is congruent to BC. And the reason for this is opposite sides of a parallelogram are congruent. Okay? Now, BD is going to be congruent to itself. That is the reflexive property. So we know that triangle BAD, which is here, is congruent to DCB. Okay, because we know that we have a side and a side and a side. So those two triangles are congruent by side, 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 congruent. And then we know that BAD is congruent to DCB. And the reason for that is because corresponding parts of congruent triangles are congruent. So we have shown the first thing that we were set out to prove. Now let's do the same process, but with the top left and bottom right triangles. So AC is congruent to AC. Again, that is a reflexive property. And if we use 2 and 6 together, again, we have shown two triangles to be congruent by side, side, side. And we can show that the angles inside those triangles are the same by corresponding parts of congruent triangles are congruent, CPCTC. And so this is the proof that opposite angles of parallelograms are congruent. And we did that by using what we know about triangles. It all goes back to triangles. All right, let's check out this proof. In example 5, we need to fill in the reasons. So we're given that JHJN and JKLM are parallelograms. H and M are collinear. Okay, they're in the same line, which means HM is a line. And N and K are also collinear, which means that this is a line. Okay. Basically, what we're showing here is that we have a straight angle here. J is a straight angle for both this line and this line. So we don't have any other angle measure other than 180 degrees for these lines. So we're going to prove that angle G is congruent to angle L. So GHJN and JKLM are parallelograms. These two items are parallelograms, and that's our given. We know that HJN right here is congruent to angle G, and MJK is congruent to angle L because opposite angles of a parallelogram are congruent. Opposite angles of a parallelogram are congruent. Okay. And let's make that just a little bit smaller so it will fit in the line. Okay. Now, HJN, which is here, is congruent to MJK. We know that because vertical angle theorem. And then J and L are congruent. Angle G and angle L are congruent. And we know that because of the transitive property. Because if we take HJN is congruent to G, and MJK is congruent to L, then G and L are congruent. And that completes the proof. So let's talk a little bit about conditions for parallelograms. And you're going to see a lot of similarities to the properties that we've already talked about. So now we're going to be given properties of quadrilateral. We'll have to tell the quadrilateral is a parallelogram. To do this, you can use the definition of a parallelogram or the conditions below. So if one pair of opposite sides of a quadrilateral are parallel and congruent, then we have a parallelogram. That's the first one. The second one is if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. If both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. If an angle of a quadrilateral is supplementary to both of its consecutive angles, then the quadrilateral is a parallelogram. So in other words, angle A here is supplementary to B, and it's also supplementary to D, the two angles that it neighbors. If the diagonals of a quadrilateral bisect each other, then we have a parallelogram, and that's our last condition. So having these conditions, we are going to do a few examples. We want to show that ABCD is a parallelogram if we know that x is 7 and y is 4. So in this case, you're basically given what the variables are. We just need to show that as a parallelogram. Well, we know that if the opposite sides are congruent, then we have a parallelogram. So we are going to take BC, which is x plus 14, and we're going to substitute in our 7. And that gives us 21. We're going to take dA, which is the opposing side. We're going to put in 7 here for x, and we're also going to get 21 here. So we have shown that BC and AD are congruent. So now let's do the same for the other sides. We know that AB is 5y minus 4. Substitute in our y, which is 4. You get 20 minus 4, which is 16. CD is 2y plus 8. So 2 times 4 is 8, plus 8 gives us 16. So, since BC equals DA and AB equals CD, ABCD is a parallelogram. And that is how you conclude that problem, is with that statement. We have shown that the opposite sides are congruent, so therefore it is a parallelogram. In example 7, we want to show that we have a parallelogram for these values. Well, we have one angle, which is G, and it neighbors these two angles. So we know that these two have to be supplementary and these two have to be supplementary. So let's test those out. So let's first of all find out what all the angle measures are. The measure of angle F equals 9z plus 19, which is 9 times 11 plus 19, which gives us 118 degrees. The measure of angle H should be the same thing, 11z minus 3, because we know that those are opposite angles. So 11 times 11 minus 3, that's 121, minus 3 gives us 118 here as well. And then finally, the measure of angle G. We would hope that it would be 62 degrees, because 180 minus 118 equals 62, and that would make our supplementary case be true. So we have 14w minus 1. W is 4.5, so we have 14 times 4.5 minus 1, and that does give us 62 degrees. So now that we have shown that everything works out, we're just going to sum up with a statement. Since 118 degrees plus 62 degrees is 180 degrees, we know that angle G is supplementary to both angle F and angle H. Therefore, we can say EFGH is a parallelogram. And that statement was already laid out here for you. All right, example 8. We are going to determine if each quadrilateral must be a parallelogram, and we're going to justify our answers. So, for A here, Our conclusion here is no, this is not necessarily a parallelogram. The reason being is one pair of opposite sides are parallel. A different pair of opposite sides are congruent. Therefore, the conditions for parallelogram are not met. In fact, let me go ahead and make this a little bit smaller. So we can put in that last statement. The conditions for a parallelogram are not met. All right, let's check out B. So for B, we do have a parallelogram, and the reason is the diagonals bisect each other. So therefore, the quadrilateral is a parallelogram. It's much easier to show that it is a parallelogram than to show that it's not. If it is a parallelogram, you just pick the condition that's satisfied and you state that as your reason that it's a parallelogram. When it's not a parallelogram, you have to state why it's not a parallelogram. What information are we lacking? Okay, so to summarize this section, here are a listing of the conditions for parallelograms. It only takes one of these conditions to show that it is a parallelogram and to make that proof valid. Both pairs of opposite sides are parallel. You have a parallelogram. If one pair of opposite sides are parallel and congruent, they both must be in place, okay? One pair of opposite sides parallel and congruent, then it's a parallelogram. Both pairs of opposite sides are congruent, you have a parallelogram. If both pairs of opposite angles are congruent, you have a parallelogram. If one angle is supplementary to both of its consecutive angles, then it is a parallelogram, or in other words, neighboring angles. And if the diagonals bisect each other, you have a parallelogram. So now that we know what a parallelogram is, and we know how to show that we have a parallelogram, in the next section, we're going to talk about special parallelograms, because you may have thought in the back of your mind a little bit here that you can have something that is not a parallelogram still be a parallelogram, because some of these conditions also apply to other shapes, such as rectangles or squares. And there's a couple of others that these conditions also apply to. So we're going to delve into that a little bit coming up in the next section.